So thank you all for joining us. I'm Nicola Asker. I'm on the Midlands branch Professional Development Network Committee for the Pipeline Industries Guild. I actually work at National Gas Transmission as well. So today, Robert, sorry. Tom just trying to join there. Robert is going to be talking to us, and he's going to be telling us all about the investigation they've done into oxygen inhibition effects on pipeline steel. So just before he dives in, just a reminder, if you can have your cameras off, mics off, and the session's being recorded. So it will be on YouTube at some point in the future once we've sort of got it all uploaded. But I think that's it. And Q&A will be at the end, so if you can try and hold on to those questions. And sorry if the chat's not quite working. But yeah, over to you, Robert.
Great, thank you, Nicola. I'll just share my screen. Let me know if that's not working, but hopefully that's now full screen for everyone. So yeah, I mean, Tom can present it if he wants, but I think it's probably best if I take us through it. So yeah, so my name is Robert Best. I work at National Gas Transmission as well. I've been there for nearly 2.5 years. My role is looking at the impact that future gases, hydrogen and a bit more on CO2 have on the materials that make up the national transmission system. So the project that I'm talking to you today is about whether small additions of oxygen can inhibit any effects of hydrogen on pipeline steels. So there. So yeah, so start with a bit of background, then talk through the experimental setup and then the results. It's quite a technical talk. I've got half an hour, I'm maybe a bit less, but I managed to put loads of slides in, so I'll kind of whiz through it. But hopefully I'll be able to answer any questions you have at the end. But yeah, go through the results and then contextualization, kind of what is it, so what, and then a few conclusions on the project that we've done. So I'll start with just a bit of introduction. I think most of the people on the call are from National Gas, so this is no surprise to you. But for those of you who don't know, National Gas, we're the national system operator for gas transmission in the UK. We've got over 7,500 kilometres of high pressure pipe operating 94 to 40 bar, loads of compressor stations to move the gas around the country. And that gas is currently used in power generation, domestic use, and then about a quarter of it is used in industrial and commercial use. Interconnectors into Europe and into Ireland, and I quite like this kind of figure down the bottom. It's a few years out of date, but I don't think it's changed particularly in the last few years in terms of the amount of energy in the gas network compared to the electricity network. So a lot of my work is all kind of looking at how do we decarbonise the UK. It kind of shows that there's a lot of energy that we need to decarbonise. Electrification is of course an option, but there's a lot of energy in the gas network that needs to be decarbonised as well. So how are we going to do that? So one of the options we're looking at is hydrogen. So the three industries I talked about, the three customers that we have, the markets we have currently, industry, power and heat, are options for hydrogen, kind of a plug and play with a few little tweaks here and there to get it to work, but it's relatively straightforward kind of switch in some respects. And another market that also needs to be decarbonised is transport. There's a huge amount of energy in diesel, petrol and kerosene, and we see hydrogen or fuels derived from hydrogen and or CO2 to be a real potential new market for the national transmission system in terms of whether that be land or air or maritime. So how are we planning to do that in National Gas? We've got a dual pathway. So we're looking at both adding hydrogen as a blend into the natural gas network. So maintaining the existing network and maintaining the same customers, but adding increasing blends of hydrogen into the network in order to decarbonise the natural gas network. But also we're looking at building out a 100% network, which is known as Project Union, which will join up a lot of the industrial clusters. I think there was a talk yesterday on the East Coast Hydrogen, which is our first section of Project Union. This is 100% hydrogen pipeline as much as we can repurposing. So my job is looking at what's the impact of hydrogen on the existing network, but there's also going to be some new build, likely to be new build pipeline. So again, my role is looking at what's the right materials and what's the right design criteria for new build pipeline. So kind of a dual approach there. Okay, so now a bit more. So my role is as focused on the materials, as I mentioned. So I'm going to talk to you a bit about what are the materials on the national transmission system, and the ones we're interested in this particular project is the pipeline, and the pipeline is a mixture of carbon steels. So this chart here is a bar chart showing the different kind of grades we have, and we've got grades from grade B and X42 all the way up to X80, and the number after the X is the strength level, so going from sort of a lower strength grades up to the high strength grades. Most of our network is X60. We've got quite a considerable amount of X52 and also quite a lot of X80, which is a bit unusual for an onshore pipeline operator. A lot of them, for example, in Europe, just have X70 as their highest strength grade. Pipe diameters go from very small to very big, and wall thicknesses as well vary. Most of our pipes are over 35% are going to be X60 of 1/2 inch and 36-inch diameter. The pipeline was constructed, the first pipeline, I think, the national transmission system was constructed in 1964. That one's no longer in use. I think the oldest one we've got currently in use was installed in the late 60s, I think 1967. But this chart just shows the kind of the growth of the NTS over its lifetime. And so we have a lot of build in the 1970s especially, and some steady growth through the 80s, 90s and noughties, and no pipeline major build since the early 2010s. So that kind of just shows you the age of the network. It's relatively young compared to other networks around the world, especially the US and some parts of Europe, but nevertheless it's still in some respects an old asset. Some of the pipes under the ground are quite old. They've been maintained and managed very well, but there's potentially some differences between the materials, whether it be X50 or X60 that were installed in the early 70s to the same grades installed in the 2000s, for example, which could be important for hydrogen service. So hydrogen and materials, I thought I'd put a slide in just to sort of set the context for the oxygen project. And as many will probably be aware, hydrogen is known to adversely affect the material properties of metals. A number of processes all kind of bundled up in the term hydrogen embrittlement. What does that mean? It means it could affect the maximum operating pressure or lifetime of the pipes that we have under the ground. There are codes that exist that are there to control this. Sort of the ASME B3112 is probably the most famous code for hydrogen, and we have an IGEM equivalent code that kind of sets some maximum allowable operating pressures, and it also gives some guidance on the material qualification requirements for hydrogen service. And there's various data to show that hydrogen, even in small quantities, can cause decreases in material performance. So this project was looking at, is there any way we can mitigate that? Are there any technologies that exist that could help us, could reduce or eliminate the potential deleterious effects of hydrogen on the materials that we have, on the steels that we have? So this project was run with Rosen, a supplier that we use a lot, and it was looking at adding very small additions of oxygen, so at the ppm level, so 50 to 1000 ppm level of oxygen. And there'd been some work in the literature that had shown that this can have an inhibiting effect on hydrogen embrittlement. So it somehow stops the hydrogen entering the steel. So this project was really looking at, okay, those tests were done on different types of steels in slightly different environments. We wanted to make sure that we'll understand whether this technology or this phenomenon exists in the types of materials that we have on our network. So we tested 3 different grades of steel, X52, X60 and X80, which, as you noticed, they were the most common ones we had on our network. Different types of welds and different types of different diameters and wall thicknesses as well. And again, materials that have been taken from different ages across our network, to really give us a broad understanding as to whether this effect is specific to particular microstructures or particular grades, or whether it's a bit more global. Testing was done in specialist autoclaves. These are not easy to find. There's not many places in the world that has capability to do high pressure gaseous hydrogen testing, for obvious reasons, the safety reasons, and it's very tricky to do. It's technically difficult to put specimens inside an autoclave and test them. But yeah, that's that. Yeah, we worked with Rosen and DNV to do the testing. These are the types of specimens we have, and you can see different, due to the different wall thicknesses, we have some very small specimens and some larger specimens. Okay, so if we jump into the results here. So I'm going to talk about fracture toughness and also fatigue crack growth rate. So just as a bit of background on what I'm talking about, so fracture toughness is a measure of the energy required to grow a crack. So if we have a defect in a material, and in these particular types of tests, we deliberately introduce a sharp defect, and we then basically pull the bits of material apart. This is one type of test, which is a bolt-loaded one, but you can also put some clevises in here and basically pull this notch and the crack at the tip there apart, and then you measure the amount of force it takes, and you can work that out in terms of an energy required to open the crack. And higher values give higher toughness, and so basically the more force it takes to open a crack, the tougher the material is, and the better it is in terms of its performance in hydrogen or in air and anything. So the data we have here, we've got the toughness on the y-axis here, and we have crack growth on the x-axis. And the ones I want to pick out are the blue line here, which is the in hydrogen performance. So the higher the better. So we get a relatively low flat curve in hydrogen. In air, which is the black dots, we get a much higher curve, and it kind of it's a steeper curve, which means that effectively we have a tougher material. We then added small amounts of oxygen into the hydrogen flow. So this is 100% hydrogen at 80 bar. We then added 50 ppm up to, in this case, 500 ppm into that 80 bar hydrogen mix, and then did the same type of test. And you can see that as you increase the amount of oxygen, the curves move closer to an in-air curve, which is the same as in methane. Methane is an inert gas in terms of material performance, so we tend to do the tests in air for ease and for simplicity, but we know that the data in air is the same as in methane. The chart on the right here shows the same data, but kind of a bit easier to understand. So again, we've got the fracture toughness on the vertical axis and the oxygen concentration, this time on the x-axis, and you can see this is the average value for a hydrogen test, just over 30, which is taken from this point here, and the air value is just under 80, which is here. And you can see that as you add 50, 100, 250, 500 ppm of oxygen, the fracture toughness is increasing. So oxygen is bringing it back to something as it would be in methane or in air. And also what's interesting is that the scatter of data is decreasing. At low oxygen ppm, we get quite a bit of scatter. Some of the curves are good, some of them not so good. But as you increase the oxygen concentration, that scatter reduces. So we've got much more. It's showing that the amount of oxygen is important in that sense. So higher toughness equals more optimized pipeline operation. So that's what we want. Now, for those of you who really wanted to see some fracture surfaces and some SEM images, this is a slide for you. So scanning electron microscopes looking really closely at the fracture surfaces. So in these tests, we pull the material apart, and then we can look at under very high magnifications what it looks like in terms of the fracture surface. And this is interesting from a material science perspective, because the type of fracture is changing as we're going through, as we're adding oxygen. So at low oxygen levels, we have this kind of faceted which is kind of typical hydrogen in embrittled microstructure, sort of a brittle-like microstructure, quite flat. As we increase the oxygen, we get a bit more of these kind of dimpled features. And again, as we go even more on oxygen, we get this sort of classic fibrous type microstructures. May not look very different to some, but these are important to material scientists. This is quite different, and it shows that the mechanism of fracture, so the way the material is behaving, is changing just by adding small amounts of oxygen into the gas. And that's obviously manifests itself with this increase in toughness, but we're showing that it is happening then. Okay, so that's the fracture toughness data. We also did some fatigue crack growth rate testing in this project. So fatigue is crack growth due to cyclic stresses. And so this could be, and in a pipeline, this is typically pressure variations as we take gas on and off the network. And fatigue is when you have these cyclic stresses, we get incremental crack growth. And so we did some testing in this. Hydrogen, again, is known to affect fatigue crack growth rate, especially at low frequencies. So what we did here is we looked at, we measured the fatigue crack growth rate, which is this on this axis here, the number of the increase in crack length by cycle, dA by dN. We did that over a number of differing frequencies, so log scales on both here. And the idea of this, it is known that the hydrogen takes time to migrate to the crack tip and cause its embrittling effect. So if you did a very high frequency test, if you cycled the material really quickly, hydrogen doesn't have a lot of time to embrittle the crack tip, and therefore the performance of the material is quite similar to as it would be in methane or in air. But as you decrease the frequency of these tests, hydrogen has more time to get to the crack tip and cause the embrittling effect. And so we like to do a frequency scan in these kinds of tests to make sure that we're testing at the frequencies that are relevant to the to our network, but also making sure that we're not testing too quickly. But the other reason for doing a frequency scan is to make sure that testing is expensive and takes time. There's no point going something really, really slow and then taking months to get the data when we could use a slightly quicker frequency. But anyway, the key from this slide is seeing that the black dots are the hydrogen performance, the pure hydrogen, and we have crack growth rates in this kind of region, the different frequencies, and you can see there's a drop 10 times or even more between the red and blue dots, which are different oxygen concentrations, and we tested it at different delta Ks, and I'll talk about delta K in a second. But effectively, over lots of different frequencies, oxygen seems to still have an effect. So oxygen is working even at the low frequencies, it appears. Another way of presenting fatigue data is in these what's known as Paris curves, and these are looking at the same data. We've got a crack growth rate here, so the number of millimeters per cycle that a crack can grow, and we can plot that against what's called a delta K. So K is a description of the stress state at a crack tip. So if you've got a pipeline and you pressure load that, there's a general hoop stress on the pipe, and if there's a crack in that, the stress or the stress intensity at the crack or the defect is intensified. So we have what's called, and that's characterized by this K term. And so a delta K is a change in K. So that could be akin to pressure cycling. So if we have a pipeline that's maybe operating at 70 bar, and then during the day, pressure gas is taken off, and that decreases down to 60 bar or something, we have a 10 bar pressure swing, a delta P of 10 bar, and then that's equivalent to, well, that then translates into a delta K, depending on the crack size, but we have a delta K. So this chart, basically these Paris charts show that as you increase that delta K, so as that that, in this case, pressure swing is increased as we go to a bigger pressure swing, we have a higher crack growth rate. And that happens in air and it happens in all materials. As you have a higher delta K, you get a bigger crack growth per cycle. And that decreases on different as the delta K decreases. So we did these kinds of tests in hydrogen and in oxygen doped hydrogen. And you can see that the hydrogen crack growth rates are can be 10 times the methane. So these are the black markers, which are the hydrogen, pure hydrogen crack growth rate, and this dotted black line is a typical air kind of value, and you can see it's quite a lot quicker in hydrogen. On the addition of oxygen, so again we're looking at 50 ppm and 250 ppm, these red and blue markers, we get a convergence back to similar to the air curve, so we're getting a much reduced crack growth rate. This is a logarithmic scale, so it's 10-20 times reduction, which is very significant. The curves tend to sort of converge at the bottom, but at these kind of levels we've got quite low crack growth rates, so it's it's more important that we have an inhibition effect at the high delta Ks. So the takeout from this slide is that oxygen additions result in crack growth rates and rates that are similar to air and methane, and that can be really important for the operation of the network. So that's a lot of sort of material science and testing, which is interesting to me, but maybe a lot of people going, well, so what? So we can take that data and plot it in terms of what we call critical curves. So these are a set of curves that describe the acceptable dimensional limits for a crack-like feature under a given loading condition. There's lots of numbers on here, but effectively we can use these curves to highlight the impact of oxygen on pipeline operation and also inspection, so integrity management. We looked at in the project, we looked at two different stress cases. I'm going to talk to you about stress case 1, which is a sort of typical transmission network stress case. So we load the pipes up to 72% of the specified minimum yield strength, and then we and in the curves we also added in the particular fracture toughness values that we measured in the project that I talked about before. So we're looking at ones that are typical of 100% hydrogen and ones that are affected by oxygen, so higher values for those. So here are the critical curves, and we've done critical curves for both the longitudinal seam weld and also the pipe body. There are reasons why they're slightly different, things like residual stress and other stress concentrators related to welds. So the welds tend to be lower than the pipe body. And these critical curves basically show that as the toughness increases, which is the same as the oxygen level increases in the hydrogen, the curves increase. I'll take away a few of those curves to make it a bit easier to understand and to see. And now I'll just plot for the longitudinal seam weld the 100% hydrogen, so the pure hydrogen curve here in yellow, and then the curve that was related to the data at 250 ppm oxygen in the hydrogen blend, and the air curve. So you can see that the oxygen and the air curves are very similar. And also what I put over is a bounding curve for the sort of latest state-of-the-art inspection technology for internal cracks, which is EMAT technology. And you can see, so basically the technology is able to detect cracks above these limits. So anything below 40 mil or so, the tool finds difficult to find, and also it is on a longitudinal seam weld, it can find cracks that are bigger than 0.3 of the wall thickness. So in this case, this was a 12.7 mil pipe that we modelled. It's actually 3.8 mil that it can detect. And you can see, so basically what the critical curves show is that if we have a defect that is of a length and a length and a depth that is above the curve, then that would be an unstable defect and something that we would need to address immediately. If it's below the curve, then it should be safe. And you can see in hydrogen, in terms of detectability, we have a very small window in terms of the sweet spot of a depth and a length that is not critical that the tool can find. For we had a crack that was growing here, it could reach a critical level before we're able to detect it. With the addition of oxygen, that same crack would grow into a region which could be detected by inline inspection, and therefore we have a much better chance of finding that before it becomes a consideration for us. So if that gives a bit of context and the sort of the usefulness of this, of being able to increase the toughness here. So in conclusion, so yeah, actually done quite well for time. So just to conclude, so the project here was working with Rosen. We did some laboratory testing looking at oxygen, and we've shown that it's effective inhibitor to hydrogen embrittlement in the lab. Improvements in both fracture toughness and fatigue compared to 100% hydrogen. We've done some detailed fractography, which also kind of looks at it at the scientific, at the microscopic level, and kind of proves out what we're seeing at the macro level on the test level. That's a start. There's lots of further work required just to confirm this behaviour over different microstructures. So we didn't test welds in this project. We did limited testing on welds. There's no reason to think that this wouldn't be effective on welds, but I think we need some data just to prove that, and maybe do some more legacy pipe grades. But again, I think we're confident that the same behaviour would occur on welds and older pipe microstructures. One of the next points is we need to prove this at a network level to understand how we could mix oxygen into the gas flow at the network level, and also over a kind of local level, making sure that we're getting mixing through convoluted pipe work, through valves and other bits that are important as well. And another thing that we need to demonstrate is that there is some data coming out of the US on this particular topic that shows, or that indicates possibly, that over very long time scales, oxygen is not quite as effective as we're seeing in the lab. As mentioned, we tried to test at the lowest frequency that we could and the slowest strain rates that we could, but we are kind of limited by the test equipment and the time and cost that entails. But there's some data to show that maybe oxygen doesn't work as well as it's showing here over a very, very long time scale. So we need to really investigate that and just prove out that the technology is something that we can use. And also there's consequences to upstream and downstream processes. Adding oxygen to the stream is not good for owners of gas storage, geological storage, who want a very oxygen-free gas to avoid any microbial activity. And obviously downstream customers in terms of fuel cell users of hydrogen want very, very pure, high purity hydrogen delivered. And so we need to make sure that we understand what the economic impacts of that, and kind of take those into account if we need purification processes or anything else to kind of clean up the gas pre and post our operation. So the final slide here is just some acknowledgements. So a big thank you to Rosen, who conducted the research on behalf of National Gas. So I worked with the Newcastle team, Neil, Angel, David, Ben and Ollie, and also they did the testing over in Lingen. Here's a picture of their test facility. So Marion, Tanya, Kareem and Sarah, thank you for their support on that. And also we ended up doing some subcontracting of some of the fatigue testing to DNV in Ohio, USA. So thanks to Xiaoji Li for supporting us with that. Okay, and on that, we've got 10 minutes or so for questions. So yeah, please put your hands up and ask questions.
Yeah, thank you very much for that, Robert. That was really, really interesting. So yeah, as you said, open to the floor and see if anyone's got questions they can share. If they don't, while people are thinking, was there anything sort of surprising that sort of came out of the results that you weren't expecting?
There was a bit we saw. Let's go back to this. This behaviour here is quite interesting. Usually, so I talked about the fact that low frequencies hydrogen, there's a kinetic effect of hydrogen, so it takes time for hydrogen to do its embrittling effect, and it tends to plateau at the low frequencies. But this particular test was a very high applied stress, so a very high stress level, we found that possibly it wasn't plateauing. So that was an interesting thing. We're still not 100% sure what's happened there. That is very high and possibly not particularly relevant. I guess what was interesting was that oxygen did decrease it. So oxygen seemed to be effective. But usually we would expect a plateau, so that was a bit unusual. We also saw some interesting results in some of the in this fatigue crack growth rate, which was actually found to be related to consumption of oxygen during the test. So we would test 3 different stress ranges on one specimen and using the same autoclave with the same gas in, and we're finding when you measured the oxygen content before the test and after the test, it had decreased quite considerably. So we were thinking, oh, it's not inhibiting, but actually the oxygen's been consumed somewhere in the process. So we're still trying to understand exactly whether that is something that would happen in a pipeline or whether it was purely a testing and it was getting consumed by the autoclave or some other reason. So it wasn't leaking because the pressure was being maintained, but it was somehow decreasing. I think Roy's got a question. Hi, Roy.
Yes.
Hi, Rob. Thank you very much. That was very, very interesting. Just wanted to know if there's any literature about potential contaminants that might inhibit this process. So sort of inhibition of the embrittlement. And maybe the results you've mentioned in the US may touch on that. I don't know. But when you're thinking about things like water and carbon monoxide, carbon dioxide, and any of the other gases that may exist in the stream, is there anything that you know of?
It's a good question. I mean, we don't want water for general reasons, and water is an interesting one in that some data seems to suggest that it increases hydrogen embrittlement. Others say it has a mild sort of inhibiting effect, but generally we don't want water from a corrosion reason. So the carbon monoxide also shows in some tests an inhibiting effect. It's less than oxygen, but carbon monoxide could do that. And there are others that kind of show the opposite. So I think hydrogen sulfide is one that would promote hydrogen embrittlement. So yeah, the impurity level is quite could be quite key on this. So maybe that is something to consider in future testing, to test a gas spec that is more akin to what we would expect for hydrogen. But generally we want quite a clean spec. Considering the upstream and downstream processes as well, they're very keen on having nice clean hydrogen specs. But certainly this is a deliberate addition of oxygen in here for this particular application. So we would need to make sure that we understand that we're maintaining a level, but also understanding what it means for the upstream and downstream customers and what additional infrastructure and do we need to remove or add the oxygen, but also monitor and make sure it's there if we're going to rely on this as a technology.
Yeah, thank you. I guess this is where the sort of real life tests would come in, because these are basically lab tests, right? And you want to then go and do the test in a real system.
And it's tricky and expensive. So we're going to look at modelling in terms of the mixing of oxygen through our network. And yeah, I think we probably need some longer term lab-based tests to understand the kinetic effect. It's quite hard. There may be ways of accelerating that. You need to be very careful when you're adding temperature in and things like this. It can affect the results we're getting. So you need to be really careful on that.
Thank you.
Thanks, Roy. There's another question, Justin.
Hi, Rob. Thank you for the presentation. My name is Justin George from Safety Engineering. One question, I'm not sure if I missed this, but was it mentioned in the presentation what the actual mechanism or the chemistry is that enables oxygen to minimize this hydrogen embrittlement effect?
As part of the project, Rosen did a literature review to kind of understand that. There's a few theories that exist. The one that I think is probably prominent is a sort of chemisorption effect. So in order for hydrogen to do its embrittling effect, it needs to get into the steel. And the way it does that is by absorbing onto the iron onto the metal surface, the free metal surface, and then dissociating from H2 into H, just a single hydrogen, so a single proton, which then can get into the steel. And because it's very, very small, it can fit between the iron atoms in the steel, and then it's then drawn to stress concentrators like a crack tip. And that's why it's how it does its embrittling in gaseous hydrogen, at least. Oxygen is shown to sort of be preferentially to fill sites on above the lattice that basically blocks hydrogen from doing that dissociation reaction. So that seems to be the kind of leading theory here, is basically it blocks hydrogen from dissociating and therefore getting into the steel. Some data that from the US seems to suggest that this is maybe not a long-term effect, it's only a transient effect. So we need to understand exactly whether that is true, and trying to devise some tests to understand that and to elucidate that. The other theory is that it creates an oxide layer, and then again the oxide layer stops that dissociation. Again, I think probably the chem absorption is a bit more likely, but yeah, I guess it's not fully understood the mechanism, and I guess that's why there's a bit of contention as to how you interpret some of the data that's coming out.
Right. Okay. I think one of the what my follow-on question from that was, so have you looked at any other gases, any other like inert gases that can produce a similar effect? Essentially, there's like safety concerns with like introducing oxygen into a hydrogen pipeline.
Yeah. That's good. It's a good question, and obviously this is very low ppm, so below any kind of flammable limit. But we need to make sure, and through the modelling, that if we're going to do it at a network level, we're not going to get local concentrations of oxygen, because we want to make sure we're well below anything from a safety reason. The idea of this is to help with the integrity of the pipe. So we need to be really careful with that, definitely. There are some other ones I mentioned before, carbon monoxide. They're less effective, it appears. We're also doing some work on another project with a chemical company in the US that are looking at that basically odorize currently, and methyl mercaptan and other odorants have again seemed to show some inhibition effects. So it could be that we can add a different chemical in. I think the same questions will still exist about how long, whether it's just a transient effect or whether it's a long-term effect. But yeah, it's certainly something we're considering, and possibly in phase 2 we may look at some other chemicals adding in, which may be more desirable from a safety perspective. I mean, oxygen's great because in terms of green hydrogen production, we're splitting water into oxygen and hydrogen, so we'll have a ready supply of oxygen. So it's really easy from that perspective. But yeah, obviously we need to make sure that it's safe and effective.
Yeah, thank you.
I think we've probably got time for maybe one more question, and Richard's got his hand up as well.
Hi, thank you. Yeah, Richard Vicarage, Cadent Gas Pipeline Engineer. Just a quick one, Robert. So you said obviously these were all done on steel samples in a lab.
Yep.
Is there any plans on doing these tests again in a lab base, or using the modelling that you talked about when we're looking at the additions that are in the pipeline anyway, such as a bit of surface oxidization, internal coatings, that kind of stuff, just to see if that again inhibits or kind of actually increases the resistance?
Yeah, I mean, I think the presence of internal coatings and existing oxides and things at mill scale and whatnot is again a bit contentious. In this particular test, the premise is that we have a defect that has started to grow, so maybe through a pressure cycle, and you can imagine that in a coating and an oxide, if you've got a defect that maybe have an oxide layer, as that crack opens up, that oxide is cracked and it's very brittle, and so hydrogen is then able to get into the crack tip. So so effectively I think we're disregarding the impact of oxides and any surface coatings in this particular case. Now, whether oxides and surface coatings can help in preventing the crack from growing in the first place is a good question, and I think it's still an open question, and I think the general feeling is that we can't rely on these on this as a technology on the native oxides and flow coatings that are currently in the pipes to protect against hydrogen embrittlement. But in other projects, we're looking at trying to understand the impacts of coatings and whether we put deliberate coatings on. For example, with girth welds, where we wouldn't have a coating, could we apply a coating that can act as a hydrogen barrier and stop the hydrogen from getting into a cracked tip? In theory, that works, but the practice is a lot more tricky to prove, I think.
Thank you very much.